Recording in progress.
Got done? Get them? Okay. Would you show me what you got for the first one? I'm seeing fives everywhere. Yay. Will you show me what you got for the second one? Four. Are we good with these? Easy problems? Know how to use your technology. Shouldn't be too big of a problem. My question is, could we have just done f of 3? We just plugged it in directly and get the same thing? Does that give us 5? Let's see, that gives us a 9 minus 4 over 3 minus 2. I think that's 5. Okay, so we can just plug that in. And could we just plug in 2 and gotten the same thing? Okay, yeah, so what I'd like you to do is make a sketch of the graph and have a discussion about why one works and why the other one does not. Ask someone to explain about what's going on here. Okay, you can help me out with this one. Yes, Nico.
Because there's an awesome code when I see this one with anything and you find the end by click on the graph and see that it'll find you.
Okay, and there's an asymptote at x equals 2, is that what you said?
X squared minus 4 is x minus 3 minus x plus 2.
Okay.
X minus 2 on the bottom, you can top and bottom.
Okay, well, we're left with x plus 2, but it remains that x cannot equal 2. Okay. So yeah, something strange is happening here. It's definitely a rational function. So they either have asymptotes or poles. Is this an asymptote? It is a hole. Okay. So when I graph this function, it is x plus 2. Are we okay graphing f of x equals x plus 2? Are you using a table of values? I hope not. We know that the y-intercept is 2. The slope is 1, so just go up 1 over 1. Go up 1 over 1, and here I am going to put an open circle, yes. And I can keep going up 1 over 1 and have a really nice graph if I were actually using graph paper, but I think I've done pretty well here. So Nico, thank you for your help so far. So in terms of that table you were looking at, it was a little tedious to type in the numbers, I know. But do you see what was happening visually here? Around that 3 and around that 2? Around that 3, all those y values are really, really close to 3. They were going to 5, weren't they? It was like 4.99 on one side and 5.001 on the other side. Because they were zeroing in on that 5, which does exist around x equals 3, but at x equals 2, like you said, there's a hole there. So even though y values are going there, they never actually reach there. But that is the idea of what a limit is. It doesn't actually have to exist where they're going, but it has to indicate that it's going somewhere. Are we good with that idea? Okay, so last time we talked about using technology to find limits. Today we're going to be using a different tool you have to find limits. It's called algebra. Dun, dun, dun. You ready? Let's go. Ready or not? Okay, this first one. So I'm going to give you a bunch of rules. Then we're going to use these rules to make new rules. And then it'll be like a rule smorgasbord that you're going to use today. None of it using technology. The first one says that the limit of a constant function, and I'm going to start here because there's a whole lot of stuff here. If a is just a constant function, will you show me what a constant function looks like? The graph of a constant function looks like this. It doesn't go up, doesn't go down. It remains constant. So I hope it makes sense that the limit as x approaches c of a constant function a is equal to, say it loud and proud, is equal to, okay, you know how to say it. It's equal to a. Like if like for instance, you don't have to write this down, but if we're talking about x approaches to the function 5, no matter what you plug into that calculator, it's going to give you 5, isn't it? The limit, no matter where you're going for that constant function, is just going to be equal to that constant number. Fair? The other one, the limit as x approaches c of just the function x. Can you show me what the function x looks like? And just slope of 1, y-intercept is 0. Do you have any idea what that limit would be equal to? Well, think about what's special about this function. If you plug in a 3, out comes a 3. If you plug in a 2, out comes a 2. If you plug in 100, out comes 100. If you plug in numbers really close to those x values, the y value will be exactly the same. So I hope it makes sense that this limit is equal to c. Whatever that x is going to. That's what the limit is. So this is kind of like, okay, we got our bread and butter. Let's build the meal. Oh, that was terrible. Okay, limit of two functions added together. It may not surprise you that it's equal to the limit of the first plus the limit of the second one. So it's not quite distributive property, but it kind of mimics distributive property, doesn't it? Distributive property really is only for multiplication, but we can consider that distributive property. Like the first two are the same. The last one, okay, these things are true. So these are all properties of limits that we can use to evaluate limits when they get a little bit more complicated. So if the problem asks you to use the properties of limits to evaluate, this is what I want to see. Notice in there we have a product. So I'm going to rewrite this as the limit as x approaches -5 of -4. I know how to write a -4 times the limit as x approaches -5 of x. You know what that first limit is? It's -4. You know what the second one is? -5. You know what -4 times -5 is? You better know. We're back to second grade for you. And that's how to do this problem. So no calculator necessary. You don't have to type in -5.00001 or -4.999995. You just do it like this. Next one, you see what we're going to do first? Actually, a couple of steps here. We could rewrite this as a limit as x approaches -2 of 3x minus the limit as x approaches -2 of 5. But that first one, -2 of 3 times limit x approaches -2 of x minus limit of 5 as x approaches -2. Do you know how to do each piece of this? Yes. I think this first limit is 3. The next limit is -2. And that last one is 5 and -6. -5 gives us -11. I know. It's incredible. And lastly, I'm going to break this up into limit as x approaches 2 of 5 times limit as x approaches 2. Now, I don't have anything for x squared. That's why I'm going to break up that x squared into x and another x. Each of which we know how to evaluate, I hope. 5 times 2 times 2. Should I distribute that 5? That'd be a silly thing to do. It's just 20. Distribution property only happens over addition and subtraction. I do see students do this, like try to do crazy things like that sometimes, like they just lose their mind. It happens sometimes, as long as you learn from it. So far, so really exciting. It's a lot of limbs, isn't it? Maybe this is the most limbs we've ever written in. Let's kick it up a notch, finding the limit of a monomial. A is a constant. X to the n is, n just represents some natural number. So in order to do this one, I'm going to, well, first I'll write it as intended. Limit of ax to the n. How many different limit statements should I break this up into? N, it makes sense, n plus 1. 1 for the a. So we have limit of a times limit of x, and this is still as x goes to c, times limit of, sorry, limit as x goes to c of x, times dot dot dot, finally times limit as x goes to c of x. And how many of these do I have? I have n of the answer be a times c. That gives us a really nice tool. You may have been saying in your mind, can't I just plug that number? Well, now that we have this, back with this, it's completely. Yes, you could just plug that C if it's a mono. You don't have to break it up into a ton of little limit statements. So we're building a structure here. So that's monomial, but how about larger degree polynomials? Well, since we already have that rule for the sum of limits or the difference of limits, as long as it's a polynomial, you could just take that C and plug it right into the polynomial. That is the limit. You don't have to do any other work. For instance, number one, how many limit statements should we split that up? Let's split that up into? None. It's we just do this problem. I would like for you to discuss the easiest way to do this problem, the most efficient way to do this problem with your neighbor.
I just have like a permanent partner, so I don't have to leave every time. Like just have. That's my job. I'm just like. Yeah, it's like plugged into the old access.
Did you get it? On the count of three, I'd like to hear you got. 1, 2, 3. Oh no. Oh no, I guess you didn't get it yet. I give you no more time. Okay, I'll give you another 20 seconds.
I can see that I get hurt.
Okay, just the first one. Okay, on the count of three, if you got it, I'd like to hear it. 1, 2, 3. 50. Are we good with that? And you got that by plugging in 2. Yes? Now, the notation of number 1 bothers me a little bit. Do you see what bothers me? I feel like it's poorly written. Yeah, it's not clear about what we're taking the limit of. I would like to see this. I think that's actually what we should all mean. Like, just kind of bothers me a little bit. Maybe that's me being nitpicky, but also it kind of bothers me that it took a really long time to plug in that 2. I understand it. I totally get it because that's a lot of work plugging in that 2. I want you to think back and see if you remember an easier way to evaluate that polynomial if x equals 2. Think about it for a moment. Anyone coming up with anything? Like, it seems like that's kind of the most direct way, just plug in a 2. And remember? I'll give you a hint. You ready? Right? Blast from the past. Blast from the past. Let's see if you can finish. Oh, the number that goes in that is 2.
Like synthetic division. I like
Just like that.
Yeah, -6, 3, or negative. Oh, I would ask.
It seems like a lot more work than just plugging into that. I feel like there's like more.
The synthetic division?
Oh, wait, I'm in, you can see
Wait,
half
wait,
this.
wait.
I'll remember being the one there. Oh.
Oh, 52.
Oh, right. Yeah. Okay, so you have to like go all the way down. Like, take forever to do that. Especially when there's like more than, I think you're right. When it's like. You're talking about the teaser.
Okay, did you get it?
Yes.
You got it? Do you want to talk me through it? Can you tell me what you did, or would someone like to talk me through it? Lydia, yes?
So like, the synthetic division, you have to like put all of the coefficients like up the top, so like 5, -6, 3, 4, and -2.
Okay,
And then, yeah, I think like you add like 5 and 0, so that's just 5, and then multiply that by the 2, and just 10, and then add that to 4, and then you get like 8, and then 11.
just a minute. Is it coming back? Did you finish it? Let's get, if they didn't finish, let's give them just a moment. I like where you're going with this stuff. Oh, good question. That's part of what was it, chapter 4? I'll give you little hints, but I can't go over why exactly. Yeah, keep on going.
This one's like, 50.
50. Nice. Does anyone remember what theorem this is called? It is the remainder theorem. So remember we talked about like the P's over Q's and trying to find the rational zeros. And we were really happy when that was a 0 there, because if you plugged in a 0, that would be, or if you got a 0, then 0 would be a remainder. In terms of why, it's a good question. It has to do with, I think, it has to do with something called nested factoring. I'd be happy to go over with anybody a little bit later if you like. But at this point, I'm gonna ask you to trust that it works. So either way, I really recommend keeping this just as a tool in your pocket. I think you're less likely to mess up for a high degree polynomial like this. Would it be a good way to do number 2? It seems like only if you really love synthetic, this is called synthetic substitution, then it'd be a good way. But I think it's pretty easy. Just plug in that -1. So we get -3 plus 2 plus 5. Did I do that right? Did I do it right? And then that gives us what, 4? Lydia, thank you for your help on that number 1, by the way. Kudos to you for keeping that. Is synthetic division, synthetic substitution, does that bring back good memories or bad memories? It seems like a gift for the math gods to me. Synthetic division. It's such a pretty little operation or procedure. But I respect your opinion. Find the limit of a power or a root. Notice neither one of these is a polynomial. So this is just saying if you have the limit of something to the nth power, you could take that limit and kind of put it into the power. That's what's going on over here, right? It's now the whole thing is being raised to the nth power. Same thing happens with roots. If you're taking the limit of a root, you could put that limit inside the root. What do you think, Nico? Makes sense? Yeah, pretty straightforward. Let's see how you would use this. Okay, number 1, shall we use binomial theorem to expand this polynomial? So we can make it a polynomial and then plug it in? Well, unfortunately, until just 2 seconds ago, we didn't have another option. But we just found out that if you have something like this, that could be rewritten as the limit of 3x minus 5 to the 4th power, right? So that's what that penultimate rule is saying. You have the limit of a function we raised to the 4th power. Just put that limit inside that thing that's raised, whatever. And now should we break that up into 3 limit statements? Only if you really like tedium. Oh, I forgot to put this, by the way. But yeah, you just plug it in because it's a polynomial. So we have, what is that? -2 to the 4th power. Did I do that right? Should I finish the problem? Because sometimes students come up and ask, do you want this or do you want me to finish the problem? And the answer is always finish the problem. Well, the answer is always, the answer always is use your best judgment. And if your best judgment leads you here, then I will help you fix your judgment. That's how it works. Hey, there's a radical. What are we supposed to do with that limit? Just put it inside the radical. It's okay. Inside, we're left with a square root of 8. Should I simplify that? Of course, we should simplify it. Or should I write it as a decimal? That's usually a bad idea unless it's a word problem or it says round to the nearest block. So yes, simplify. Oh, I forgot to mention, there's more to up here. There's the last statement. The second limit statement up there is only true if certain condition holds for the values of f(x). What do you think has to be true for these values of f of x? Well, it can't be negative. So f of x must be positive. It could be equal to 0 if, I'm sorry, I'm going to say it. I won't be lazy here. The limit must be greater than 0 if n is, what's the word I need? If n is, think about it. Are negatives ever allowed? What is it? What? Even, thank you. I hope that makes sense. We know cube roots of negative numbers. They exist. Cube roots of, square roots of negative numbers yield imaginary results. And we're not going into imaginary. That's only with solutions of polynomial equations. On to over here. Okay. Is this a surprise to you? Yeah, these are very, very straightforward. The only thing is you have to be careful to make sure that what never happens denominator is never 0. So this is only true if the limit as x approaches c of g of x is not equal to 0. If it's equal to 0, yeah, some more work to do. And if it's 0 over 0, use your algebra. To get out. And the teachers on the team were very insistent that they never want to see 0 over 0 as an answer or as part of the process even. So what I'm going to do is I'm going to put this like in a thought bubble here to say we thought about it, but we didn't write it down. So if you put 0, 0 as an answer, there's going to be a problem unless you acknowledge that it's not actually part of your answer. A thought bubble could help. So what do I mean here? Okay, well, example 1. Notice, is there a problem with the bottom? As x goes to 1, there is no issue. So we just proceed. The bottom is 7. The top is 5 minus 1 plus 2 6. 6, I get that right? Okay, yes, no problem there. But how about the next one? Dun, dun, Hey, look at that denominator. That's not good. Finding that limit as x approaches 3, right? So in our heads, we're breaking this up. Limit as x approaches 3, x squared minus x minus 6. I should do this a little bit better. Full problem on top. And I was a little bit lazy with the last one, my limit statements. I apologize. And I was also lazy with my parentheses. Okay. Equals 0 over 0. Oh no. Oh no. I'm just thinking it. I'm just thinking it because I acknowledge that this means I need to do a little bit of algebra. I think you already know the algebra we're going to do here, don't you? It's called factoring. So we can simplify. So my algebra work, x minus 3, x plus 2 over x minus 2 times x plus 2. Put this on the side. Oh, they're 3 and 3. Thank you. I was stuck on the warm up. Did I get the top one right? South. Parentheses around that fraction. No, it doesn't help. The fraction groups itself together. And now, if I just plug in the 3, well, do I get zeros anywhere? No zeros anywhere, so I could plug in the 3. So from the original graph, what we're looking at is a hole where there's nothing there, but we're looking at the simplified form of it. So this is equal to 5 over 6. Okay, quick look at this. You see, we're not going to write it, but you see the 0 over 0. Oh, that's no good. We have to get out of this with some algebra. Please take a moment to discuss. How are you supposed to get out of this with algebra? So what do we do? What do we do? Can we square it? Can we square top and bottom? Is that a property that a over b is equal to a squared over b squared? Can you just do that? It seems like it's appealing. It doesn't work, unfortunately. If you try to just square the pieces, also if you square that top, you're left with a trinomial. So it's just so difficult. Any other ideas? When you're changing a fraction, you could just multiply by one thing, correct? You could only multiply by 1. What's that? X minus 3 over x minus 3. X plus 3. These are good ideas. What we're going to do is multiply by the conjugate of the top. Just make sure your neighbor knows what a conjugate is. It's been a while since we talked about these things. This is going to be square root of x. What is the square root of x? Plus square root of 3. This should be a pretty quick process. Let's see if we could navigate through it without falter. Anyone finish? bottom. Go back. Distributing on the bottom, you're gonna get much work. Please go back. Yeah, on here, oh. Check with your neighbors, see if they were able to get through this algebraic conundrum.
All that.
So I didn't see.
Yeah.
Reach on the bottom. That's right.
You do not. You can if you want. If you want to have fun. I know you like it. Did you get it? Did you get the new form? So the top becomes x minus 3. And the bottom? X minus 3 times root x plus root 3. At the top, we multiplied it out, and it's nice to multiply out because the two expressions are, well, conjugates result in, I'm sorry, I should say conjugates result in a difference of squares. That's why it's no more square root on top. Bottom is just a mess if you multiply it out, plus you lose that factor, right? So nice. Leaving us with this limit as x approaches 3 of 1 over root x plus root 3. And now? Plug in 3. So this is 1 over root 3 plus root 3. Do we know what root 3 plus root 3 is? 2 root 3. 1 over 2 root 3. Should we rationalize? I've told you again and again, no need to rationalize unless it says rationalize. We're done with that problem. I'll give you a moment to work on 3. I would like to call someone for this. Check in on your neighbor, make sure it's going okay. Get it? Lydia, you've been chosen. Can you help us with it?
Okay, so I saw it as like a factoring by grouping problem.
Oh, nice.
And like you can do it for also these non-numbers too. So, like the factor kind that I got was, like on the top, I got x squared plus 4 times x minus 2. Over x cubed plus 1 times x minus 2. And then, because like, that is getting work normally, that you have to kind of total out x minus 2. And then you can plug into the other one.
You got what?
8.
8/9. Do we agree? Thank you, Lydia. That was fine. Any questions? I did forget to mention this one fun thing. Does it make sense that you could think of x minus 3 as a difference of squares? And it's not like obviously a difference of squares, but if you think about it as a difference of squares, that means you could factor it into. Check with your neighbor. How do you factor it if it's difference of squares?
Yeah, it's fine. So,
So the first factor would be root x minus root 3 times. That is a nice way to do this, isn't it? If you think about it that way. So you could use either the conjugate or you could force a difference of squares into something that isn't naturally difference of squares. And etc. I think you get the exact same thing. Well, you better get the same thing. One last thing. And then you have time to work on your assignment. After this, find the limit of an average rate of change. Okay, rate of change is just another way of saying slope. Like when this interval a to b means I have the point a comma f of a. Does that make sense? Because it's from this function. I forgot to say that. The function f of x, so if x is a, then y will be f of a. And then for the other coordinate, it's going to be b comma f of b. So hopefully you can see that this is just exactly what you've learned in Algebra 1. This is y2 minus y1 over x2 minus x1. Yeah? You know, it's f of b minus f of a over b minus a. So in this example, find the limit as x approaches 2 of the average rate of change of the function blah on this interval from 2 to x. So I'll go ahead and make this interval from 2 to x. Average rate of change is saying to find the limit as x approaches 2. So I know this is a novel problem for you. I'm just going to follow my nose. And we're going to have more insight into this in the coming days. This is a very important problem. Right now we're just looking at some mechanics of it. Limit of the average rate of change. So the top, I'm going to start with f of which one? 2 or x? The following exactly. It starts with b, doesn't it? So I'm going to start f of x minus f of 2 over x minus 2. I hope that you see I'm just putting the pieces where it's telling me to put them. We know that f of x is x. You're right, we need to get some specifics here. Do we know what f of 2 is? Show you synthetic substitution. Right, poor decision. So minus 10, I believe, over x minus 2. Now notice as x approaches 2, if I try to plug it in, I'm left with a ghastly quantity. 0 over 0. You don't like. I'll let you finish this problem. Just like now with this. Sure. Want to check and get in, make sure they're okay. Lydia, you'll never guess what you. Never guess. He's holding. Look at that. Now you wouldn't have guessed. You probably would have gone over here if you would have guessed. Yeah. Okay, hold on.
Yeah, so basically, backtrack is Raven, so it's x minus two times. Thanks, x minus two on the fucking model cancel. And then just back with the x opposed to five.
Do we agree? Fantastic. You want to take a minute to stretch or just discuss this before your work on your assignment? You could do that. But nicely done with these limits. Oh, tests are coming next time.